So we have this question. The question says, looking through the C2 and C3 bond of 2-methyl butane, which is isopentane, draw all the Newman conformations and identify the most stable and the least stable conformer. Then the B part says, use the information below to make a quantitative plot of energy versus angle of rotation through the C2-C3 bond. Then the information is CH3 eclipsing. It is 11.0 kilojoule per mole. Then HH eclipsing as a proton-proton. It is 4.0 kilojoule per mole. Then CH3H eclipsing is 6.0 kilojoule per mole. So it's kilojoule per mole here. And then CH3 gauche is 3.8 kilojoules per mole. So the first thing we have to do is to first draw the Newman projections of the 2-methyl butane. So this is a normal butane. And so a 2-methyl butane looks like this. So this is the C2 and then the C3 bond. So let's draw all the Newman projections of this molecule. So for the carbon facing us, which is the C2 carbon, it will be a dot. And then the one at the back is the circle, which is the C3 carbon. I'll see that the C2 carbon is bonded to 2 methyls and 1 proton. So we could say this is one of the methyls of the C2 carbon. And so the other methyl, we could bring it here as a CH3. And then we could put the proton here. Then for the carbon at the back, which is the C3, it is bonded to only one CH3. So we can put the CH3 here. And then it is bonded to 2 protons. You can see that the protons of that carbon have been shown. So we can put 1 proton here and then the other proton here. So this is the first conformer. Then from this first conformer, we can go to the next conformer by rotating the 60 degrees. So this is the C2 carbon. And the C2 carbon is bonded to a CH3. And then a proton here and then a CH3 here. And then the C3 carbon is the circle. We are rotating 60 degrees, so the CH3 will come here. And then this proton goes to this side. And then the proton here comes down here. So this is the second conformer. We can go to the next conformer by rotating another 60 degrees again. So this is a CH3 and this is also a CH3 and this is a proton and then this is a ring. So this is the carbon in front. So the carbon at the back, we are rotating another 60 degrees. So this CH3 will come here. So here will be a CH3 and then this proton goes to the top. So here's a proton and then this is also a proton, which is here. Then from here we can go further and draw the next conformer by doing another 60 degrees rotation. So let's come here. So this is a proton. This is the C2 carbon. CH3 is here. And then another CH3 is also here. Then this is the carbon at the back. So remember we are doing another 60 degrees rotation. So if we are doing another 60 degrees rotation, the proton on top here will come to this side. The proton that was here will come here. And then the methyl group that was over there will come to down here. Then we can continue again by doing another 60 degrees rotation. So this is the C2 carbon, and then this is the C3 carbon. So here is CH3 again. Yes, also a CH3, and then this is a proton. And when we rotate, this CH3 comes to the side. So here is a CH3, and then here is a proton, and then this is also a proton. Then we can do further rotation again. So we draw the Newman projection, the conformer. So this is the carbon in front, C2 carbon, this CH3, this also is CH3, and this is a proton. And this is the carbon at the back. So this is a CH3, and then this is a proton, and this is also a proton. So these are the Newman projections that we can draw. So these are all the conformers of 2-methyl butane. So we can see that this is 0 degrees, and then this is, so let me write it on top. This is 0 degrees, this is 60 degrees rotation, and then this is 120 degrees rotation, and then this is 180 degrees rotation. This is actually the anti-staggered conformation. And then from this 180, we'll come to a 240 degrees rotation. And then from 240, here's a 300 degrees rotation. And from 300 degrees, we go to 360 degrees, which is the same as the 0 degrees rotation. The B part of the question says that use the information below to make a quantitative plot of energy versus angle of rotation about the C2-C3 carbon-carbon bond. So now he says that CH3-CH3 eclipsing is 11.0 kilojoules per mole. So let's take this molecule. You see that in this molecule there is a CH3-CH3 eclipsing. So it means that the energy here is 11.0 kilojoule per mole. So 11.0 kilojoule per mole here. And then he also says a proton-proton eclipsing is 4.0 kilojoule per mole. It means that here is also a 4.0. And he also says that a CH3H eclipsing is 6.0. So this side too is a 6.0. So if we add all, so a 6.0 plus a 4.0 is 10. 10 plus 11.0 will give us 21.0 kilojoules per mole. So the energy for this molecule, so let me write it down here. For the 0 degrees, we are having 21 kilojoules per mole. Now let's come to here, this side. You see that here is a CH3 gauge relationship. So, and then for a CH3 gauge, it is a 3.8 kilojoules per mole. So between this and this, we have a 3.8 kilojoules per mole here. And then between this is also another gauge between a CH3 and CH3, and that is also a 3.8 kilojoule per mole. So 3.8 plus 3.8 equals 7.6 kilojoules per mole. So it means that for the 60 degrees, we are talking about a 7.6 kilojoules per mole. Then let's come to this side. This side, the relationship is a CH3 gauge. That is the only energy we find among what was given here. And a CH3 gauge is a 3.8. So this is a 3.8 kilojoules per mole. Now, that corresponds to 180 degrees. So 180 degrees is a 3.8 kilojoules per mole. And then let's go ahead and come to this side. So for this side, we have a CH3H eclipsing, and we also have a CH3H eclipsing, and we also have a CH3H eclipsing here. So here is a 6.0 kilojoules per mole. This side too is also 6.0, and then this side is also 6.0. So 6.0 plus 6.0 is 12.0 plus another 6.0. That is 18.0, and that corresponds to 240 degrees. So for the 240 degrees conformer, we are having an 18.0 kilojoules per mole. And it is understandable because you can see that that is an eclipsing conformer. And then let's come to this side, which is the 300 degree rotation. So for the 300 angle, you can see that we only have this CH3, and this CH3 gauge relationship is a 3.8 kilojoules per mole. So for 300 degrees, let me write it on top here. So 300 degrees corresponds to a 3.8 kilojoules per mole. So for the 120 degrees, you see that we have a CH3H eclipsing here, and that is a 6.0. And then we have a proton-proton eclipsing. Proton-proton eclipsing is 4.0. And then we also have a CH3 eclipsing. CH3 eclipsing is 11.0. So we have 6 plus 4 is 10. 10 plus 11 is 21. So there's a 21 kilojoules per mole for the 120 degrees. So 120 degrees also corresponds to a 21 kilojoules per mole. So you see that there are some similar energies here. For a 300 degrees is 3.8 kilojoules per mole, and then 180 degrees is also a 3.8 kilojoules per mole. So in the energy profile diagram, both the 180 degrees and then the 300 degrees will have the same energy. And also at the 0 degrees is 21 kilojoules per mole, and then the 120 degrees is also 21 kilojoules per mole. So on the energy profile diagram, both the 0 degrees and the 120 degrees will also have the same energy. So let's go ahead and then plot the energy profile diagram. So this is how our energy profile diagram will look like. So the 0 degrees was 21 kilojoules per mole, 60 degrees was 7.6 kilojoules per mole, 120 degrees was 21 kilojoules per mole, 180 degrees was 3.8 kilojoules per mole, 240 degrees was 18 kilojoules per mole, 300 degrees was 3.8 kilojoules per mole. So if we come here, this is the dihedral angle. Remember, it is from 0 to 360 degrees. And then the 0 degrees and the 360 degrees are the same conformers. So they are going to have the same energy profile energy. They are going to have the same energies. We are going to plot their energies against the dihedral angle. So now, 0 degrees is 21 kilojoules per mole. So this is 20. 21 is somewhere here. So if we match them, and you see that the 0 degrees will be somewhere here. So 0 degrees, and let's plot the 60 degrees angle too. So for 60 degrees, the 60 degrees corresponds to 7.6. So this is 6. 7 is midway. So 7.6 is near 8. So it's going to be somewhere here. And then for the 120 degrees, we have 21 kilojoules per mole. This is 20. And this is 22. So in between 20 and 22 is 21. So which is somewhere here. And then the 180 degrees is 3.8 kilojoules per mole. So this is 2, this is 4. So 3.8 is almost 4. So it's a little bit less than 4. So it's somewhere here. And then 240 degrees had 18 kilojoules per mole. So this 240 degrees. And then 18. So this is 18. So 240 degrees. It's going to be somewhere here. And then 300 degrees. 300 degrees was 3.8 kilojoules per mole. So 3.8 kilojoules per mole is somewhere here for 300 degrees. And then the 360 degrees conformer is the same as the 0 degrees conformer. So that one too will be 21 kilojoules per mole, which is somewhere here. So connecting all the potential energy diagrams, we are going to get something like this. So we have to connect all of these points together. So this is the energy profile diagram for 2-methyl butane. How to convert a molecule in perspective into a Newman projection. So for example, let's assume we have a molecule in this perspective form. How do we convert this molecule into a Newman projection? To convert a molecule from a perspective form to a Newman projection, for example, remember that in Newman projections, we have the front carbon and then the back carbon. So now, if we divide the Newman projection vertically into two, then all the groups that comes at the top and then the bottom are the atoms that are in the plane of the molecule. The plane of the molecule. And then all the groups that comes to the right hand side are the dash bond. The dash bonds are the bonds that are going into the plane. So for this bond and this bond, they are going into the plane. And then on the left hand side, the bonds that are put on the left hand side are the wedge bonds. And then the wedge bonds are the bonds that are coming out of the plane. So let's draw this molecule in Newman projection. So this is the front carbon. So this is the front carbon. And then this is the carbon behind. So this is the carbon behind. And then we've said that what comes on top are the atoms that are in the plane of the molecule. In this case, chlorine and chlorine are in the plane of the molecule. So it means that for the carbon atom in front, in its plane of the molecule is going to be chlorine. And for the one at the back, here too is going to be chlorine. Now, then we say that those that are on the right hand side are the dash bonds, which are the bonds that are going into the plane of the molecule. So the groups of atoms that are going into the plane of the molecule is the C2H5. So it means that for here is going to be C2H5. And then what is coming out of the plane of the molecule is the proton. And that one is supposed to come on the left. So there is a proton here. And then for the carbon at the back, you see that it is the proton that is going into the plane of the molecule. So it means that this side is a proton. And then C2H5 is coming out of the plane of the molecule. So it's going to be on the left hand side. So here is going to give us C2H5. So this is the Newman projection of this perspective molecule. Let's take this molecule and then convert it into a Newman projection. So this is a perspective molecule. Let's convert it into a Newman projection. So this is the carbon in front. So we represent it by this dot. And this one is the carbon at the back. So this is the carbon at the back. And remember, we've said that for the plane of the molecule, it is on the vertical axis. And then the plane of the molecule is protons that are on the plane of the molecule. So this is the plane of the molecule. So this proton is here, and then this one too is here. And then we said that on the left-hand side are the bonds that are going into the plane of the molecule. So they are the dash bonds. So on the carbon in front, you see that the group on the dash bond is what? The bromine. So it means that bromine will come to this side. And then what is coming out of the plane of the molecule is the chlorine atom. So, and then that one comes on the left-hand side. So here's the chlorine. And then for the carbon at the back, proton is on the dash bond and proton is also on the wedge bond. So that means that on the wedge bond is this proton. And then on the dash bond is also this proton. So let me draw it. It looks like this. So this is the Newman projection of that molecule that we see in perspective. How to convert from the chair conformer to Newman projection. So let's assume that we have this chair conformer. How do you convert this chair conformer into Newman projections? So what we need to do is that we need to hold the molecule at these two sides. When we hold this molecule at these two sides, you see that these are the carbons in front, and then these are the carbons at the back. So now, we'll be able to draw the carbons in front and the carbons at the back, and then link the various atoms that are connected to it. So now, we see that there is a proton in an axial position here, and there is a proton in an equatorial position here, and then there is also a proton in an equatorial position here, and there is a proton in an axial position over there. So now, you can see that this looks in the form of Y, the carbon in front here, and the one here also looks in the form of Y. So what we need to do is that in drawing the Newman projections, let me draw the Newman projections here. We need to draw a Y here, and this is the carbon in front, which is this carbon. And then at this side too, we need to draw another Y. So this is the easiest way to easily convert the molecule into a Newman projection. Then, so this is this carbon, and then this one is this carbon. Now, if we start with this carbon, you see that the proton, this part is this proton. So we put this proton here. And then this part is this OH. So there's an OH here. And then this part is CHF. Remember, there is a proton in the axial position over here. So here is CHF. Then now, let's draw the carbon at the back, which is this one showing the carbon at the back. And the axial position, there is an C carboxylic acid group. So at this part of this molecule, there is a carboxylic functional group here. And then you can see that to this part is a proton. So this side is a proton. And then this side is a CH2, because there is a proton in an equatorial position here, and then one in an axial position over there. So that's a CH2. So to this side of the molecule, we have a CH2. Then when we come to this part, you see that down here, which is this portion, is the CH3. So there's a CH3 over here. And then to the right hand side is a proton. So that is this part. So to this right hand side is a proton, and we have a CHF to the left hand side. So you can see the CHF already there. So let's draw the carbon at the back. So this is the carbon at the back. Now you can see that to the north, to the upper part of that carbon, we have a proton. So there's a proton here. Then to the left, we have a CH2. You see the CH2 is already there, so we need to just connect these two. And then to the right, we have an ether functional group. So this ether functional group is over here. So you can see that this is how you convert a molecule in a chair or a chair conformer to a Newman projection. What about this molecule? So let's consider this example too. Let's convert this molecule into a Newman projection. So the best thing will be to fill up the missing portions or the missing proton on the molecules. So you see that there is also a proton in an equatorial position here and another one too at this place. Then this is a CHCl and then this is a CH2. So now you can see that this looks as usual. You need to first draw Y. So there is a Y here. And then at this part of the molecule, at this portion to we'll draw a Y. So there's a Y here and there's also a Y there. So this represent the carbons in front, which is this carbon and this carbon. So let's start with the carbon at the left hand side. So you see that to the left hand side, it is bonded to an OH. So there's an OH here. And then to the right hand side, it is CHCl. Because remember, there is a proton in an axial position over here. So here is a CHCl. Then the down part or the bottom is a proton. So we are done with this carbon. Let's come to the carbon at the back. So this is the carbon at the back. The upper part is a bromo group or a bromine. So we'll show the bromine there. Then to the left hand side is a proton. So this left hand side is a proton. Then to the right hand side, you can see a CH2 here. So this is a CH2 at this portion. Then let's come to this carbon. The down part is made up of a proton. So this is this proton over here. Then the right hand side is a CH3 group. So this part is a CH3 group. Then let's come to the carbon at the back. So this carbon, which is this, the upper part is made up of a CH3. So this is a CH3. So CH3 is over here. Then the right hand side is a CH2 and the CH2 has already been shown. So we'll just connect it to this. And then the right hand side is a proton, which is this proton. So this proton has to come to this side. So you can see that we've been able to convert that molecule or this molecule into this Newman projection. So let's convert this molecule to a Newman projection. You can pause the video at this time and then try. So just as we said, let's fill in the missing portions. So you see that there's a proton here and also there's a proton here. There's also another proton here and then there's a proton here. Then there's also another proton here. So now, just as we said, we need to draw the carbons in front by first drawing a Y. So this is our Y. Then you also draw a Y here. So having drawn the Y's, then now when we come to this carbon, so you see that the down part, which is a proton. Then on the left hand side, it is another proton. So this is a proton. And then on the right is a CH2. So this is a CH2. Remember, there is a proton in the equatorial position and another proton in the axial position. It's the same thing over here. There's a proton here and then there's also another proton here. So let me cancel this out. So this is a CH2. So this is a CH2. Then now let me straighten this line. So this is CH2. Then now let's draw the carbon at the back, which is this. You see that to the left hand side is an OH. So this is an OH. And then to the right hand side is a CH2. So there is another CH2 over here. And then let's come to this part, which is this. The down part is a proton. And then to the right hand side is a CH2CHBr. So this side, which is the right hand side, is a CH2CH and then a Br over there. Now let's draw the carbon at the back, which is this carbon. You can see that to the right hand side is a proton. So there's a proton here. And then to the left hand side is this CH2. So let's join it to this CH2. And then the top part, at the upper part is a CH3. So there's a CH3 over here. So you can see this is how you convert that molecule into a Newman projection. Let's convert this molecule into a Newman projection. So we just have to continue by supplying the missing portions. So there's a proton here, there's another proton here, and then there's also a proton here. So now let's draw a Y. We always begin with a Y. So this is our Y. And then we also draw another Y over here. So you can see the bottom part here is a proton. So this proton. And then to the left hand side, there's an OH here. And then the right hand side is a CHOH. So this is a CH and then OH over here. And then let's draw the carbon at the back, which is this carbon. The upper part is a proton. Then to the left is also a proton. So there's also a proton here. Then to the right of it, this is a tet butyl group. So let's draw a tet butyl here. So it is a CH33. So this is a tet butyl group. We are done with this side. Then we come to this part. So the bottom is a proton. Then to the right, there is an iodine group here. Then let's draw the carbon at the back, which is this carbon. The upper part is a proton. Then to the left is an OH. So there's an OH here. And then to the right is a tet butyl group. So the tet butyl group is what has been drawn here. So there's a tet butyl group here. So this is how to convert this molecule into a Newman projection.